or the history of the atom. There's four guys, Democritus, Lavoisier, Joseph Proust, and Jonathan Dalton, that have kind of come up with the concept that we now actually call Dalton's atomic theory. Democritus was the first one to mention the concept of atoms, tiny little things called atoms. He did this back in 400 BC. Of course, Aristotle didn't agree with him, so that was thrown away. Antoine Lavoisier was the first one that carefully weighed reactants and products in chemical reactions and found that the mass is neither created nor destroyed, so we give him credit for coming up with the law of conservation of mass. Joseph Proust came up with the law of definite proportions, which basically states that different samples of the same compound always contain the same proportions of each element by mass. What does that mean? That means if I have a little bit of water or if I have a lot of water, I'm still going to have roughly 88.9% oxygen and 11.1% hydrogen. Dalton kind of stole all three of those guys' concepts and threw it together into what we now call the atomic theory. He said that each element is composed of tiny little particles called atoms. He stole that from Democritus. He said that all atoms of a given element are identical and atoms of different elements are different, which is not necessarily true because isotopes are atoms of the same element, and they're not necessarily identical. They have different masses because they have different numbers of neutrons. He said atoms are not created or destroyed in chemical reactions. They are dissociated, combined, and recombined, which is kind of a little bit of a steal from Lavoisier's law of conservation of mass. And then finally he said compounds are formed when atoms of different elements combine with one another. A given compound always contains the same relative numbers and types of atoms, which is once again him stealing from Proust. Then we get to J.J. Thomson. J.J. Thomson used a cathode ray tube, which is a vacuumed tube that sends a beam of particles. And he added an electrical field to it, and he noticed that this beam of particles bent towards the positive electrical side. So he said that these atoms must have some sort of subatomic particle within them that has a highly negative charge to it. So we give him credit for coming up with the electrons. Ernest Rutherford was one of the first to work with radioactive material. He put a radioactive source inside a lead block. This radioactive source sent off particles in this direction. He set up a magnetic field similar to what J.J. Thomson did. And he noticed that the beta particles bent towards the positive magnet. The alpha particles bent slightly towards the negative end, and then the gamma particles went straight through. So he pretty much said that these atoms are consisted of things that have negative charge, things that have positive charge, and things that don't have any charge whatsoever. Then he did the famous gold foil experiment, in which he did the same thing. He used a radioactive source, and he shot alpha particles at this gold foil. And he noticed that the majority of alpha particles went straight through. He also had this kind of fluorescent surrounding that would spark every time that a particle would hit it so that he could actually tell what's going on. Then he noticed that 1 out of every 8,000 would kind of deflect off to the side. And then 1 every 20,000 would return back and deflect at an angle greater than 90. So what did he say? He said, first of all, that the majority of an atom is empty space. That's where the electrons hang out. And he also said that there must be some sort of dense, compact center in the middle of these atoms, which we now call the nucleus. The nucleus is a very small, positively charged core containing the protons and the neutrons. Negatively charged electrons are extremely tiny and occupy the majority of space of an atom. So we've got 3 particles, subatomic particles, protons, electrons, and neutrons. What's the charge of a proton? +1. Electron, -1. Neutron, 0, no charge whatsoever. The mass of a proton we call 1. The mass of a neutron is slightly larger than the mass of a proton, but we can call it 1. It's close enough. There is mass to an electron. It's very, very small, like 0.0005 AMUs. So it's small enough that we can still call it 0. So how are we going to figure this out? We have two pieces of information that we find on the periodic table. The mass number, which is equal to the number of protons plus the number of neutrons, and the atomic number, which is just equal to the number of protons and the number of electrons if carbon is a neutral atom. So the mass number, which sometimes they call A, is 12, carbon 12, and the atomic number, which we sometimes call the Z number, is 6. 6 protons, 6 neutrons, 6 electrons. This is carbon 14, which would be considered an isotope of carbon. Isotopes are atoms of the same element that have the same number of protons but different number of neutrons and therefore different mass numbers. This would have 6 protons, 6 electrons, and 8 neutrons. This is hydrogen 1, atomic number 1, mass number 1, atomic number 1. So it has 1 proton, 0 neutrons, and 1 electron. Now on the other hand, hydrogen 2 is going to have 1 proton, 1 neutron, and 1 electron. This is called deuterium. Isotopes, once again, of an element have the same number of protons, different number of neutrons. Isotopes of an element exhibit identical chemical behavior. This is why H1 and H2 both bond with oxygen to form water. When it's bonded with H2, we call that heavy water. Carbon 14 and carbon 12 can both bond with oxygen to form CO2. The mass of one carbon atom is exactly 12 AMUs. All other atoms are measured on the scale that is relative to carbon 12. The average atomic mass that's given to you on the periodic table is an average. For example, silver 109 and silver 107 is really silver 108.90476 and silver 106.90509. This one is found in nature 48% of the time. This one's found in nature 51% of the time. It's almost a 50-50 split, so I'm going to guess that the average mass is somewhere in between there, so kind of like around 108. Okay? The way that you solve for this is you take the mass times the percentage, of course in the form of a decimal, take the other mass times the percentage in the form of a decimal, and then you add them together. And we should get an answer around 107.87. So we're going to do another one. This one's for chlorine. We're going to take the mass, 34.969 times 0.75, 36.966 times 0.2422, and then we're going to add them together, and we get 35.45. Lithium has 2 naturally occurring isotopes, lithium-6, lithium-7. Its average is 6.94. So now we have to find the percentages. So I'm going to take 6.02 times, I don't know, some number we'll call x. I'm going to take 7.02 times, well, that would be what? 1 minus x. Because this is a percentage in the form of a decimal. Let's say it's 0.25, 25%. Well, then this would be found 75%, or 0.75, so 1 minus it. So we have, they're going to use y instead of x. Oops. 6.02 times x plus 7.02 times y minus x. Carry all of this out, and we solve for y, and we get 0.08, which means 8% lithium 6.02, 92% lithium 7.02.